We'll still wait a few more minutes, because so far we are 12, including moderators, 9 participants. So if there were 20 yesterday, maybe we'll want to wait a few more minutes. So it seems we lost. It seems that the references in C++ pushed away half of the participants. It would be interesting at the end to find out if this session about C++ is more challenging to C developers or Python developers or Fortran developers, or if there's no real difference. Regardless where you come from, it's like a more or less unified difficulty. Certain programming languages already have certain features that we're going to use in C++ with a different syntax. But if you come from C, let's say, there are new concepts that you need to get your head around. So maybe it's a bit more challenging, same for Fortran. So that would be interesting to see the gymnastics needed.
I mean, my experience, but yeah, that would be good to also to hear the thoughts of the rest of participants. The jump from C to C++ is quite easy, I would say, because the syntax is the same. You only, with C++, you need to be aware of the object orientation programming, other ways to do the same that you can do with C, but I would say that the syntax is the same. Coming for Fortran, the change would be like a more challenging, and I would say that there would be even more if, well, I would say that maybe from Python is even more challenging, but I mean, definitely from C is like, I would say that is the easier, but I mean, happy if someone disagrees, please say so, and yeah, happy to discuss, but yeah, this is just my opinion.
Okay, it was interesting also yesterday to see the little discussion that was going on in the chat between Python programmers. Discuss the function overloading feature in Python and the ways it could be done in Python. So that was nice. So we'll see if something similar happens today. 15 participants, so it sounds like that's getting about right. Maybe a few more, and we're good to go. In the meantime, I guess I'll start sharing my screen, so that in case there's a last-minute surprise, I will know it now. Okay, we have the wonderfully recursive screen. Amazing. Can someone try to send a message in the chat to check if I get the audio notification? Oh, perfect. So this time I do get the audio notification. Great. One good point for Chrome. Okay. Let's wait a couple more minutes and then we're good to go. Yes. So I will share my screen so you will have the slides displayed on my screen as well. But if for some reason you want to run the slides locally, Kevin and I have put again the link in the chat. So feel free to check that on your screen and stay synchronized with the audio if you just want to have your slides. I must say I cannot know. I did not create those. This is a question.
I can answer the well. I can this is a combination of Markdown and also where the slides are showing HTML, but I think it's a little bit it's a JavaScript library that takes Markdown and converts to HTML. To be honest, I also like if you want to have more details about that, I will send you the link to the repository where you can find more.
There's a link about the slides. Otherwise, you can always, well, I mean, there are the contact details of Rupert Nash, who is the person who I believe created the slide.
Yeah, but I mean, in the repositories you can find, I'm pasting the link. I think, yeah. Also, we are good to start. I think we have enough number now.
Topic of C++ scientific. Yeah, I would say templates actually, when it comes to performance, is one of the very useful C++ features. So actually, the fact that it misses templates is in itself not having lambdas. As far as I know, lambdas are not a game changer for performance. C++ templates can really have a big impact. Yes, but oh, five past 2. I think we can now start. So welcome for this session, which I believe is your third, maybe fourth, not third, I would say. So I gave you the very first session on the introduction to C++, modern C++. And yesterday you've learned in the afternoon how to create your own objects, how to play with constness to declare your variables const or not, how to play with references as well, using the ampersand symbol. So you've learned how to encapsulate your data and build entities from the data you want to put in them. Today, we're going to build on this and see how we can actually start now stacking data using containers, and then the different containers you have at your disposal, but also how to then, of course, go through those containers using loops and iterators. So in C++, you will see that for each of the three containers, loops, and iterators, there are multiple ways and multiple implementations, each offering different features. So all this is available. So we're going to cover a few of all the options you have. And just like yesterday, if I happen to talk, for example, too quickly or somehow I'm being vague or inaccurate or something, please just say it. I will come back, reformulate, or I will try to speak slower. Okay, everything's fine for everybody? Seems so. I continue to abide by the same philosophy. If I get no messages, it means it's fine. Okay, so again, the slides that I will show you today have been made by Rupert Nash. The second session yesterday. I would think so. No, but I think there was a second one in the afternoon. TBC, to be checked actually. So yes, Rupert Nash has done these slides. So I'm Ludovic Kepley, I'm not Rupert Nash. So if you have any questions how the slides were made, again, we can see it later, and I guess Rupert will be the best person to ask. So in C++, a container, you can instantly understand that a container somehow is going to hold an object. Okay, what do we mean by uniform type is something that can quickly get a bit multiform depending where you're coming from. But let's say just of a uniform type as in a single type. Okay, it's not exactly single because if you have polymorphism, for the people who know that, you may, let's say for now to simplify, uniform type. Owns the object that it contains. This is very important, the notion of ownership. Because now that you've learned how to create classes, then you know that you have constructors, you have destructors. Because variables have a lifetime, remember? So for example, when they go out of scope, they can be destroyed by calling the corresponding destructor. And what happens is, when you're going to pass, to use a variable in a container, to add a variable in a container, the container gets the ownership of that variable, meaning it will be in charge of calling the destructor. Meaning, if you pass somehow a reference on a variable, stay aware, remain aware, keep aware, stay aware that this variable might be deleted by the container. The container somehow gets out of scope itself. So that's one of the potential tricks. But of course, containers also provide you access to the elements. So different containers will provide you with different features. All of them provide access, but different types of access. We're going to see that in a few seconds. Questions here? Okay, slides, perfect. So,
Ludovic, sorry for
yes,
interrupt.
no worries.
Just like an advice, please ignore the chat. In case that there is something important, I will let you know, okay? And just keep
Okay.
going with because there are some questions, but I will answer them, so are not, let's say, that relevant for this. So in order not to interrupt the flow, please keep talking, and I will interrupt you in case that there is something that you need to address it. Does it work?
Perfect. Yeah, I was so used not to have the audio notification yesterday that I was just going back and forth. But yes, for
Yeah, if
someone
you
looking at
want,
the
feel
will
free
be a
to
bit helpful.
disable it, and I will let you know if something needs your attention.
Thank you. So only slides now. So in C++, you have a certain number of container classes. Okay, template classes. We're not going to see all 13 of them. We're just going to see the main ones, the ones you're actually very likely to use at some point. And they also cover a wide list of available features. So you will understand the different approaches to each data structure, which you are likely to have seen in the programming language you know, regardless which programming language it is. So the one we're going to begin with is the vector. So unlike the classic array, which I guess you've all had by now at some point, the vector, the size of the vector is determined at runtime. And the memory is allocated then. I'm going to come back on this runtime memory allocation in a few minutes. When we say that the elements in a vector are contiguous in memory, it means that they are next to each other in memory. Okay? That's very useful for performance because when you have an element, you know that the following element is right next to it in memory. So it's very quick to move from an element to the next. So when you're iterating your vector, this is very useful. We'll come back on resizing a vector in a few seconds. You have here, first of all, a quick code. You have here an example of a vector. So just like yesterday, if you want to include the vector, first you call the pragma, okay, which is a preprocessor directive. We've seen that yesterday. So the hashtag include angle brackets, the name of the library, and the closing angle brackets. Okay. Then the IO stream. Why? Because we want to print to the terminal, and we've seen namespace, colon, and then the standard output. Okay, output stream, so the terminal in this case. And the way you declare your vector is std : vector. So far, nothing surprising for you. You know that it comes from the standard library, so namespace for standard library items, std : You say that it's a vector, so far so good. And then between angle brackets, again, you give the type of the data you're going to put in the vector. Because of the templates, the fact that a vector can be a vector of any type. So it can be a vector of doubles, it can be a vector of integers, it can be a vector of strings, it can be a vector of anything you want. You just have a few conditions to tick, but for the time being, any type you want. So that's how you create a vector. And this function getData, you just assume a function that, for example, reads data from a file and returns a vector of integers. Okay, so that's how to declare it. And then that's one of the ways to iterate it. We're going to come back on this in a minute, don't worry. That's one way to iterate it. Like for each integer that you would name x in your vector data, then you just print x to the terminal, followed by line break. Okay, which in C++, as you've seen yesterday, the line break can also be used can also be obtained using std : end l for end line, so endl. That's another way to do it. That's a bit more C than C++, but it absolutely works well. So that's really the first aspect of vectors, really how they are used and the fact that I have contiguous elements and their size is determined at runtime. That's fine. But now, vectors are actually used because they provide you with nice features. Of course, you can access randomly any element by indexes just like you can do with classic arrays. Okay, you can copy and move. Again, nothing special here. The resizing is an interesting one. So when you normally declare your array, let's say an array of 100 elements, number one, you need to know that size before you allocate, which makes sense. But then you can't expand it. You can somehow reallocate it somewhere, but you can't expand it. Vectors respect the same rule, but they can do that for you automatically. We're going to see why and how. We're going to see how when we try to insert elements. Because when you will insert elements, if there's not enough space, the vector will dynamically reallocate space if needed, taking care of everything that's done in between. Again, we're going to show that. See, that thing is in the next slide. And then we have the element deletion. Of course, you can remove an element in the middle of the vector, and the unused element will be then overwritten because it will just shift everything coming after. So when you have an array, classic array, of 100 elements, if you remove an element at the position 53, you have to manually shift all the elements coming after. In a vector, it will do that automatically for you, probably using a smart technique such as chunk moves instead of manual writes, for example. Something that I said just before about ownership, will be reminded here. When the container, here in this case the vector, reaches the end of its lifetime, understand, goes out of scope, or you manually destroy it by calling the destructor of the vector somehow, the elements contained are destroyed. Okay, so make sure that you've got the data from the vector before the vector goes out of scope, for example, which is I think the most probable reason why a vector would be destroyed. Okay, it just goes out of scope. Now, this last line here is maybe not obvious, but I said I would explain this resizing side of things. So how does a vector work? There's no magic. It must somehow have a buffer allocated behind the scenes. But by default, since in a vector you can add elements at runtime dynamically, it cannot predict the number of elements you're going to put in it, especially if you put them one by one. So what it does is that it begins with a pre-allocated buffer of, say, 10 elements, which are contiguous in memory. Again, contiguous in memory. There's no hole between the elements. And you insert your elements, and when the 10th slot, the buffer is full. So next time you're going to want to insert an element into that vector, the buffer behind the scenes, being full, will have to be expanded. Two ways to do this. Either the memory after it happens to be free, because not used by any other program in your computer, in which case the operating system will say, oh, okay, I can just keep the buffer here, we'll just expand the end limit here. So you just get the extra elements without having to move anything in your RAM, in your memory, okay? But if you're not lucky, the elements after your buffer are already taken due to another program, for example, that stored some data in it. So you cannot allocate the extra elements you need somewhere else in memory and keep the first ones here, because remember, they have to be contiguous. So you cannot have a jump in the middle of your buffer. It has to be a single buffer of consecutive elements, no holes. So what happens is it's going to find another place in your memory, another location in your memory that will contain enough contiguous free memory. Okay, so if you had 20 elements, typically the way it works with vectors is that when they run out of space, they double the size of the allocated buffer. So if you had 10 elements and you run out of space, behind the scenes, next time you try to insert, it will try to reallocate to 20 elements. So if it has to find another place in another location in memory, it will copy the first 10 elements to the new location. So this copying that is happening behind the scenes. You don't see it, but it is happening. Again, there's no magic. Depending how you put your data in a vector, it might become a bit of a challenge. Because you had 10 elements, you insert now an 11th element, so you are unlucky, there's no free slot afterwards, so you have to reallocate somewhere else and copy. You now have 20 elements total in the buffer, so you use 11, 12, 13, and so on. You're full again, and you try to insert an element again. So you have to find now a 40-element contiguous free location in memory. Copy your 20 existing elements, and then put the new element you just inserted. And you can imagine that if you keep doing that, you will have a certain number, log2, a certain number of reallocations and copies that will happen when you will try to put your data in it. That's not really a problem when you have 10 elements. It can become a bit of a problem when you start to have a few billion elements, or a few millions, because you have all these copies that happens that could have been avoided if you know from the start, for example, that you will have 3 million elements. You can use vectors in a way to tell them directly, allocate for 3 million elements. That's a bit more advanced. Not complicated, just a bit more advanced because we don't see it first, but you can definitely do it. So you know how to declare your vector. So here we say unsigned. Unsigned implicitly means unsigned integer. So it's equivalent to type unsigned space int. Okay, it's just shortcut. So that's how you declare a vector. Okay, and that's how you append a new element. That's how you add a new element at the end of your vector. Push back. Okay, you push and the back. It's just one keyword to remember, pushback, but it's fairly intuitive. Your vector dot pushback and the element you want to put at the end. Okay, you can access the number of elements in the vector by calling size. Again, fairly intuitive. Maybe it's not the exact same keyword depending on the programming language you come from, but size or count or length is always the keyword typically to get the number of elements in an array. So that was for the vector. You have the array, not the classic array that, well, same classic array, not the actual notation you use when you use malloc in C, for example. That's the C++ array. Again, there's no magic behind the scenes. It's an array, okay? Just a more C++ notation that takes care of the malloc for you, for example, and things like that. It also gives you then a nice interface to get, for example, the size of your array, which is always useful. And for array, really, it's nothing different. You call your preprocessor directive with array. You declare it this way to say you want an array of integers in 3 dimensions. Oh, 3 dimensions, sorry, of 3 elements. And that's it. An array of 3 integers. So far, so good. Remember that it's contiguous like the vectors, okay? But the size is fixed as compile time, which is the difference with vectors, okay? With vectors, if you don't know the size at compile time, it's fine. It will dynamically reallocate anyway. You can insert dynamically, it's fine. But yeah, this is the consequence. You can't change the size. If you say it's 100 elements, it's 100 elements, period. Now something different, the lists. So the lists, you may wonder actually why we would like to use lists. So for those of you who don't know lists, lists are made of elements which contain, I will use the term pointer, I hope it will not be confusing, which contain a pointer to the next element. So each element has a value, such as the integers we were talking about with arrays a few seconds ago. So it has a value, an integer, for example, and a pointer to go to the next element. So the advantage with lists is that you can afford not to have a huge contiguous memory in your RAM. For example, if you're asking for a contiguous chunk of memory of 200 gigabytes, let's say you have a node with more than 200 gigabytes of RAM, the operating system might tell you, I don't have 200 gigabytes in a single contiguous chunk. I have 200 gigabytes in total, but in multiple locations. Lists allow you to do that by putting, let's say, 50 gigabytes of contiguous memory there with a pointer to the other location where there was another 50 gigabytes of contiguous memory free, and so on. So lists allow you to bypass these contiguous limitations that you may encounter when you have large buffers to allocate. The ones I mentioned when I said you have a buffer to the next element are single linked lists. Why? Because you can just move from an element to the next always in the same direction. If you want to be able to move in both directions, then you have a double linked or doubly linked list. Okay? Lists are very useful for insertion of elements, especially in the middle, because unlike vectors and arrays, where if you want to insert an element at position, say, 13, you have to move all the elements that come after by one slot to create an empty slot and put your value. With lists, you can just see it as cables. You have houses with cables. So if you want to insert yourself between two houses, just cut the cable, pull it, use it in your own house, and then you're good to go. You don't need to move any other house. So linked lists for this is very useful. But when you want to search, if you want to get, for example, the 13th element in your linked list, you cannot directly go to it because you don't know where it is. When it's contiguous, it's easy. You go to the start of your buffer and you just count 13 times or 12 times the size of the integer that you have put in this array, and you know that the 13th element will be at a corresponding location. When it's not contiguous, you have to go to the location of the first element. You know it's not the one you're interested in, so you go and follow the pointer to the second element, which is still not the one you're interested in, third element, which might be somewhere totally different in memory, and you just keep jumping. So if you have millions of elements, you don't want to use a linked list. If you can afford to use a vector or an array, depending on your assumptions. Again, with data structures, there are two factors in the decision making. First, whether you know them or not. You can't leverage features from vectors if you don't even know vectors exist in the first place. You will never use vectors. Second, you might say, yes, but linked lists are slow if we need this and we need that. It will depend on what your application requirements are and the characteristics of the data handling, the data movement, depending on how you are going to interact with your data, whether you know the size at compile time, at runtime, if you need to resize on the fly, if you need to insert in the middle of the data, or if you know it's always appending at the end. All these little questions. If you know the answers to these questions, then you'll be able to make a more efficient choice in the data structure you're going to use. Again, C++ offers you a wide list, a wide variety of choices for containers. You are able to make use of any of these, but then it comes down to whether you make a smart choice or not. So that's what these sessions are designed for, to help you know about these choices and then know when to use them to make the best of them. The set and the map. So these are probably, so if you're coming from Python, for example, you are probably very familiar with these. So they are associative containers. Okay. So about the red black tree implementation, that's something else, a bit more detail. If you don't know, you can search for it. It's very interesting to see the red black tree, the self-balancing trees. Very interesting part of data structures and algorithms. But here, for the sake of this session, set, map. Let's see what they are. So the map might be the most intuitive. The map is just, as I said, an associative array, meaning you're going to have an identifier and a value. So it can be, for example, a customer ID and the value being all the information about the customer, like a customer object, for example. It might be an identifier that is an integer, it might be a string, it might be a double, it might be any type. Okay? Again, you have a few checkboxes to tick if you want to use fancy types to make sure that your type can be compatible with being an identifier, but for the sake of this session so far, you can put any type. And the value, again, can be anything you want, an integer, a string, and so on. The set is like a map in the sense that you have a list of what we can see as identifiers or keys, but you don't have the values. You're just interested in having a list of, well, not a list, not a linked list, a list of elements that are unique. So sets can be useful for this, because of course the keys are unique. Since they are used, that's why I tend to use the term identifier. Because if you would have twice a given identifier, you wouldn't know which element you're supposed to get. So one identifier, they're all unique. This line here is the one that you need to take care of if you want to define your own key type. So I said to keep it simple, I won't go into details about this today. Don't worry, one of the links I gave you yesterday, the CPP reference website. I'm losing light, interesting. In the CPP reference website, you can find all the documentation you want about how to create your own key type and how to iterate through it. We're going to see that in a minute. So everything you can find online. Whether you use an ordered or unordered version of the map is your decision to make. Your decision to make, sorry. There is reasons, there is rationality why sometimes you may want to use ordered or not ordered, but again, that's more details, more contextual, so it will really depend on the use you have. So I won't go into details again for this, but know that at least now you're aware that you have these two options of having the elements sorted on the key or not sorted. Impact on performance, locality, predictability, and so on. So that's an example of what you can, I was going to say map, what you can use maps for. Maps can be very useful to decompose a mesh in 3D by saying, okay, this element contains all these triangles. Okay, so in this case, the key would be the identifier of the element, let's say an integer, and the value would be an array or vector of all the triangles. Give me a second, I'm going to turn the lights back on because I guess it's going to be a bit dark if I stay without this. So in the meantime, you can look at this great image, which is actually a real-world scenario image. We really use that for scientific computing, which I bet you know a lot about already anyway. So you know what I mean by this. So this is how you use a map, for example. So the map, you need to give two types. Remember, in the vector or in the array, you just give one type. In the map, you need two types. Y, well, the type for the identifier or the key, and the type for the value. And that's exactly how it works. std map, type of the key, type of the value. Okay? So you can access it in two different ways. The way we show here, which is, I guess, the most convenient, is just to call your map and square brackets and the index of the identifier or the key of the element that you want to access. Okay? You see the auto keyword has been used to replace the extra this that we would need normally to put on the left side of rank 2 comms. So it can make your life easier. We're going to show this again later. Don't worry, we're going to cover this. For the time being, let's focus just on how to declare the map. Okay? This one, yes, it kind of repeats what I was saying. You have different choices. Each container has different versions, different features, weaknesses, and strengths. So it depends what you want to use. I like the always, you don't need lecture, just use vector. It's vectors can be very useful. They are very efficient. in many situations. But again, if you happen to find yourself in a rather exotic context with programming challenges you're facing, you might want to use a different container. Up to you. At least now you know a few of them. So now that we know how to stack our objects or types, integers, and arrange them in containers, now the whole point is somehow at some point to go through the elements in that container. Loops is one way to do it. So we have three types that we're going to see today. You probably know at least one, maybe two, and likely all three already, depending where you're coming from. So the first one is the while. Very intuitive, very simple. While a given condition holds, you execute the code in it. Again, very simple, nothing fancy here. This is the example that was given a few slides ago about prime numbers when we were illustrating the use of vectors. And that's how you would use a while loop in this case. Again, this is fairly simple. I don't think it's something new to you, but as I said yesterday, we start from scratch, so we really make sure we cover everything from the beginning. Range-based for loop. This, again, I think in Python that is intuitive. If you know JavaScript, for example, PHP, you always have these for each loops for each set element and so on. In C++, we have the equivalent now. I don't remember when that arrived. Maybe C++ 11 again. We need to double check this one. So the notation, the syntax, doesn't change the keyword. It's still for. But what's inside, again, when you read it, it's rather intuitive. For each integer that you will call x, that is part of the vector data, do this with x. Again, very simple. You just have to remember the syntax, type, variable name, colon, container name, if it's a vector. But apart from that, it's fairly simple. You know now this, the ampersand, because here there was no ampersand, and now you know exactly what it means because you know the concept of references. So here you are taking a copy because it's no exception. If there's no ampersand, it's a copy. So you're taking copy. If you just want to display it to the terminal, it's fine. You don't need an actual reference. If you want somehow to use this notation to go through your vector and increment, let's say, all the elements of your vector, you need to make sure you use a reference. So in this case, using this ampersand. So here we are doubling the elements in the vector, incrementing, doubling, any modification to the element. Okay, so make sure you don't forget that ampersand symbol. So you can technically, using this notation here, you can iterate through any type, but remember I was always mentioning these little checkboxes that you need to make sure you tick. This is one of the checkboxes. So you have to make sure that you have a member function called begin and end. We're going to explain what these do when we'll reach the iterators phase at the end. All the STL, so STL standard library, standard template library, all the containers have this. So the four we've seen today have this too. The vector, the array, the lists, and set/map. They all have that. And of course, you're welcome to start overloading things. You know overloading as well now, so you know it can be fun and you can do many things with it. So the last one is rather simple. You're likely to know this one already. So if you come from C, you know it. If you come from Fortran, it won't really disturb you a lot. I think the gymnastics will be fairly easy. In Python, I guess you must have something very close as well. So this will be very simple to all of you. In C, the for loop can be written in this format. So three parts in this for loop, separated by semicolon. Okay. The first part is the declaration. So you say, okay, let's declare an integer called I start at 0 the second part is the condition. So while I is strictly lesser than the number of elements in the vector data, the third phase then concludes by specifying the increment. So at every iteration, the variable I will be incremented. So at first it's 0, then it will become 1 for the second iteration, and become 2 for the third iteration, and so on. So here we use a zero index because remember that in C and Python and C++, it's 0 indexed. So if you come for Fortran, remember that again, 1 indexed in Fortran, 0 indexed in C and C++ and Python. So these loops, I said, were fairly intuitive. The iterators might be a bit less, but again, you will see that there's no magic. It's not that complicated. Just go through it step by step. Do we have any questions so far on the containers or the loops before we go to the iterators? Is everything going well so far? I'm not talking too quickly. I'm not being too technical or not technical enough. Let me come back to the chat for a second.
Yeah, there is a question in the chat about the hash function.
Okay, previously it was mentioned that we need to have a hash function. I mean that we need to unique key hash for each other. Yes. So if you want to use a special type, for example, a color, okay, you created a class that represents a color. So it has a red and a green and a blue element, RGB, classic, and you want to use that as the identifier. The C++ compiler is fine with you having this as an identifier, but it must be able, behind the scenes, to determine from what you will give as the key, the position in that map. So if you pass, for example, the variable, the color black, so 0 for red, 0 for green, 0 for blue, from this, it must be able to say, oh, that's the element 14. You see? So you need to provide this function that we call a hash function, which calculates the hash, so the fingerprint of, in this case, a color. So maybe you want to add, or that would be quickly more tricky. Be careful when you define your hash function not to have clashes. Because, for example, with my example with colors, if I just add the red, the blue, and the green together, then I say, okay, so if it's 0, 0, 0, then the sum is 0, that's element 0. Fine. What happens now if I have 1 in the red? So 1, 0, 0. If I sum everything, it gives 1. Okay, so red would be in this, well, dark, correct, would be in the first element. But if I pass red, green, blue, if I pass 0, 1, 0, the sum would also be 1. So the two colors, 0, 1, 0, 0, and 0, 1, 0. Oh, you lost the screen sharing again. So it seems that it's when I come back to the original conversation that it just goes away. Okay, interesting. Is it better now? Yeah, well, no, I think you would quickly see if it's recursive. Oh, yes, that's because I came back on the chat. I was on the slide, and when I asked for questions, since you expressed yourself with messages, I came back on the chat to see if there were messages, such as the one from Alexandra, for example. Do we have any other questions on the map, sets, lists, contiguousness of vectors and arrays, but not lists? Or everything is fine? It seems everything is fine. So unless someone is writing a long message, I think we can move to the iterators. And again, if you have any questions while I'm talking, Juan can take it up. And if need be, we can also reply it. So it's no problem. Iterators now. We're going to see what these begin and end actually are. So you know this. already. We've seen that a couple of slides ago. Okay, declaration, condition, incrementation, and then your access. Now the thing is, if you want to use iterators, it would look like this. So I will explain what iterators are after reading this line, because it still is rather intuitive actually. So we're going to declare a variable. Remember the first part before the semicolon. The second part is here, and third part is here. Nothing is different. There's a line break, but the structure is exactly the same. We're going to declare an iterator. We're going to see what it is in a few seconds. So I'm going to start at the beginning of the data, and while I haven't reached the end, I'll just go to the next element. So now let's see what it means behind the scenes. The way I expressed iterators last week was, you can think of iterators as arrows above your vector, in the case of vector iterators. So you have your 10 elements, let's say in your vector, and you can see an iterator as an arrow pointing at the start of an element. So there are predefined iterators in a vector. There is begin and there is end. Begin is an arrow that points at the start of the very first element in your vector. And end is the arrow pointing at the end of the last element. So your entire vector, all your elements, are contained between begin and end. Any byte of data outside this interval is not in your vector. So what you say here is, give me an iterator, so an arrow, and initialize it at the beginning of my vector. So you place your arrow at the start of the first element. And while you haven't reached the end, you just keep going to the start of the next element. Now, why do we have this notation here to actually access the element? Why can't we just type it star equal to? It's because an arrow behind the scenes, again, as I said, there's no magic. That's what you're learning these days with this session, is that there's no magic. An arrow is just a pointer to a corresponding element. So the arrow, by definition, by default, just contains the address of that element. So if you want to actually access the value of that element, you do the same you would do in C with pointers, which is called dereferencing. Dereferencing the pointer, or the arrow, or the iterator in this case. Okay? So that's referred to as the old-fashioned C++ way. Why? Because of this, now you know that it can be replaced with auto. So auto will just deduce that begin is the iterator on data which happens to be a vector of int. So it will automatically calculate the type, deduce the type of the iterator called it to be an std vector int iterator. It just saves you time. This and that is, in this case, strictly equivalent. You might have, again, when you start playing with cards and things like that, you might have different behaviors, but for the time being, same. Exactly the same way that you can implement your own key type in maps, for example, you can implement your own iterator, but the same way that when you implement your own key type for a map, you have to implement your own hash function. When you implement your own iterator, you have to make sure that it takes a few checkboxes, which are the ones shown here. Dereferencing, incrementing, assignment, and inequality comparison. So these just allow the arrow that you're creating to, number one, point to a given element, but also give access to the corresponding elements by dereferencing, being able to move to the next element, okay, and being able to, of course, get a new value for the assignment. But the inequality comparison, why do we need to provide this? Because remember that arrows are going to be moved until they hit the end arrow. So then you must be able to compare two arrows to make sure that they're not pointing at the same position. Because if they are, then it means at some point we'll no longer want to continue. So these are the little checkboxes you need to implement. Again, it's not very complex, just a few functions to implement, but you need to know about it. Because if you try to use your iterator straight out of the box without doing that, then you're going to have a certain number of messages from the compiler saying, I can't use your class as an iterator. I'm missing this, 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 and that. Okay? So now you have 40 minutes for the exercise, so that's plenty of time. So first, let's have any more questions. Yes, we do. Why would one want to use their own iterator? Any use case? Yes, because you might want your iterator to have extra features. For now, oh, that'll be interesting. Let's see. An iterator, normally, when you increment it, for example, that's just an example, okay? When you increment it, it just goes to the next element. That's it. And when you dereference it, it just returns the value that it points to. That's it. But now let's say that you are trying, for example, to actually it'll be a smart use. That'll be a smart use of iterators. Let's say that now you actually want to check the frequency at which elements are being accessed for profiling reasons, for example. So you want to check in your vector if you have certain elements that are being accessed much more often than others. You can implement your own iterator. And then in the dereferencing function that you provide, the one that says, oh, when you have an arrow, this is how you get the element, the function that you will provide to do this will, at the end, indeed, return the value that is being pointed to. But before doing that, it will just increment a variable stored somewhere else in your program that says, oh, this element, well, the element at this index has been accessed one more time. So then you can have some logs as to how many times each element has been accessed, for example. Or you may want to use, I don't know, to do a backup. When you move to the next element, you may want to somehow erase the element that has just been read because you're using something else than a vector. Remember, the iterators are not to be used for the vectors or anything. They're to be used for the for loop. But the actual type that you pass an iterator on can be anything. So you can have your own type, like a circular buffer in something, which would automatically free the element that is behind the iterator. Like, let's say a linked list. You have a linked list. I will reply to a question, Josh, in a few seconds. I'll read it after. In the linked list, you might know that your linked list will be iterated only once. Each element will be read only once. So to make sure that you're not having any memory leak, you might want to use your iterator to move to the next element and immediately free the memory of the previous element so that it can be reallocated for something else. That could be another use for implementing your own iterator. Are there equivalents to Python generators? The object being iterated over maintains the state of the current position. If you had about iteration over an object partway through and then carried on another loop, oh, okay. As far as I know, no. And in this case, with this notation, I guarantee no, for a reason, which is if I here use another for loop, since this variable is declared inside the for loop, it will go out of scope when the curly brackets is reached. So for the next for loop, it will be a totally different variable. Now, if the variable was declared before the for loop, yes, it would remain, it would remember the state. It would be in the state. Why? Remember, an arrow is just a pointer. So yeah, an iterator, which I refer to arrows, behind the scenes are just pointers. What are pointers? Variables that contains the address of another variable. When we increment an iterator, what it does behind the scenes is it just updates that pointer value. So it says, oh, you were pointing at the address at this location in memory. Now you want to point to the next element. And since it's an iterator on integers, that's why we say an iterator on a vector of integers. Since it's an arrow that points to integers, we know that the size of an integer is like, let's say, for example, 4 bytes. So if I want to update the pointer that is being used behind the scenes by the iterator, I will just add 4 to the address. So you're pointing here, so you update it, you're now pointing there, update it, you're now pointing there, and update it. So it means that this variable always contains the updated state. Begin and end never move, unless you manually resize the container, of course. But if you don't resize it, they don't move. But any iterator you declare, yes, you're actually modifying the iterator's state every time you update it, every time you increment it. So you would definitely have the equivalent to Python, yes. Any other questions? Yes, can iter be used? Yes. As long as you provide the 4 functions specified, you can create an iterator for everything. C++ is all about interfaces. That's the whole strength of object-oriented programming in general. We don't really mind how things work behind the scenes as long as we have a given consistent interface. As long as you provide the interface that allows me with an iterator to do plus plus, to increment it, or to compare it and to read the value and so on, I'm fine with what it is you do behind the scenes with that iterator. So any type of container is fine, yes. So now you start to see all the combinations you can get going. You can do with iterators, because now you are able to build any type of data you want using classes. You're able to make collections of them in any way you want using arrays, C++ arrays, vectors, lists, set, maps. And you can now iterate through them in multiple ways. And all that now can be arbitrarily defined by you. So you can create classes based on anything you want, using them in containers, any container you want, and you can iterate them using your own iterator if you want. So you have now a full freedom, and that's the whole point of templates, which is you abstract the notion of type behind a template. You say that's a vector of some type. As long as this type that you put in the vector has these, and these properties, I'm good to go. Make sense? Well, good. Any other questions? Because I think that 30 minutes for the exercise is going to be plenty of time. So since it seems that we're all good, just in case, this is the link to the exercise, in case you didn't have the link already. So the exercise contains 3 parts. It's not very clear at first, so it contains 3 parts. The first one will be to implement the function getEven. So sorry, before that I should maybe explain the overall structure. So you will find the instructions here anyway. So you have 2 files, vector x and a file test cpp. So in the vector x, you have to implement this function here. So the one that is provided to you. So it takes a vector, and we expect that function to return another vector that only contains the numbers that are even. Okay, so all the odd number, I don't want them at the end in the vector that is returned by this function. Okay, now when you will have done this, I'll just give you all 3 phases, and then we can go step by step. That's the first phase. The second phase will be to print everything that is in a vector. But since it has to be done in a very specific way, the string that you produce has to respect certain characteristics. Otherwise, the test will fail, even if you did actually print all the elements. You know, it's just a matter of putting a square bracket, and commas between your elements so that the string that you produce at the end can be compared to a reference. And the last one, and then I come back to the chat to see what generated that audio notification. The last one will be to interact with a map. So to create a function that will take a map and a value, the map will be identified by a string. So the key is a string, and the value is the length of the corresponding key. So in that map, if I insert, for example, the word hello, I add the element corresponding to the hello record. The key will be hello, and the value will be 5. 5 letters in hello, 5. So that's the last function that you will have to create. Let's see, what's the question? Can I ask one general thing about the code structure? Is it correct that I should declare function in class in HP? Yes, fine. This code is yes, but the same as yes, all can be used in HP. Yes. Yes, that's, you covered all aspects of it. Yes, that's what Juan said exactly. That's the comprehensive exact way to say it. All the declarations should be in the header file. So header file .h, or in C++ .hpp. All the definitions, declaration definitions, all the definitions should be in the corresponding CPP file. And then the header file can be included in any file you want. Yeah, so the way it works is when you will compile a program, you will actually pass to the compiler the CPP file. The header file, HPP, is just used to declare the interface to your function. Remember when I was talking about interfaces for iterators? That's exactly what header files are here for. Just declaring your functions. Oh, this function, if I take this example, for example here, if I go to the header file, this one, this function takes a string. So in this case, it will be used to represent the terminal, but to be a bit more flexible. Sorry, I'm not pointing to the right function. This function here, this function here. It takes a vector on an integer, const reference, and it returns a vector on integer. I don't need to know what it does inside it. That's the job of the function name to tell me about it, and ideally, in a perfect world, the documentation, which is something you should do as well. But then the actual implementation of getEven is something that I don't mind. Which algorithm you use behind the scenes to extract the even numbers in the vector is irrelevant to me. I just want to have the result at the end. So that's why there's this clear distinction. When it comes to the compilation and linking phase, and yes, it's a bit trickier. Okay, great. So you now have the link to access the exercise. So feel free to get it started. The easy one is the getEven. The medium one is, well, it's easy, medium, hard, really. The hard one is because it's hard to know which prototype you need. So let me give it to you. Because what happens is when you compile, the test.cpp expects certain functions to be defined. Three of them, the three I mentioned, the one that extracts the even numbers, the one that prints all the elements in a vector, and the one that adds an element to the map and automatically put the value in it. The first function and the second functions are already provided in the header file. So the test.cpp knows the interface to these functions. But the test.cpp also calls a function for the last one, but it's not provided in the exercise. So that's why I provided it to you here. The last function needs to have this following declaration. Okay, so it's a map that has a string as the identifier, and an integer as the value. Okay? So that's the map that contains already a certain number of elements, and this will be the new element you want to add in this map. Now, something else. This map, this function, as you can see, returns a Boolean. The value of the meaning of this Boolean will be if the element that is identified by name, so by quote name, in this source map already exists, you return false. If it does not already exist, you insert it and you return true. Okay? Again, don't worry if you have any questions. If you forgot what a given function should do and it's not clear in the instructions, feel free to just post a message in the chat and we'll happily help. So now we have 25 minutes for the exercise. So make sure that if you feel a bit lost or anything, say it. It's the perfect opportunity to do so. Yes. So that's a tricky one. In this case, you don't need an iterator, you need a const iterator. I think it's that's the notation, I think. Because I may be confusing with Qt, so give me a second. Yeah, that's the one. Okay. Yes, because when you say an iterator, that's again one of the advantages of using iterators, which relies on the on the object-oriented programming, is that these are objects, so they can be more complex than just a raw pointer. One of the things you can do with it, like a const pointer, after all, is by default an iterator can modify the value that it points to. But if you don't want that to be a possibility, you need to say that you don't want a classic iterator, but you need a const iterator. Congratulations. And it also means that you can create an iterator when you're doing your own. You can create an iterator, a const iterator, but you can also create another type of iterator if you want. You can invent a new type. A backup iterator, that every time an element is accessed, it just logs it. Or a monitoring iterator. Or a single pass iterator that could be optimized for single pass transversal. Actually, yeah, we could have plenty of fun just with implementing customized iterators. Who has finished the first exercise? I guess probably everybody by now. If someone is stuck, feel free to say it. Make sure that you don't stay silent. Again, that's exactly why we're here, to make sure that you get the help you need. Yes, yes. So let me give you this. Okay, so the thing is, yeah, that's a bit tricky. Give me a second. because in the tests, when it compares, you see, yeah, that's why. So that's okay, that's fine. So that's the format that it expects. Okay, it's always, so it starts and ends with square brackets. Okay, but then it's always space, number, and a comma if there's a number coming after. Okay, so if you pass this, it will not be happy because it was expecting this. So that's why I say, all in all, if your test is failing because of the actual formatting, that's fine. But the test again will quickly complain if there's one space missing because it will say that the strings produced are not, technically speaking, identical. Ah, okay. So I'm just struggling with getting the current iteration value to format the last entry. So how do you mean? Oh, making sure you don't have an extra comma at the end, for example? Oh, so that, okay, cool. So that has nothing to do with the iterates. Well, for this, you may want to use a Boolean. So you have two ways to do it. The most intuitive way is probably doing backwards. Yes. So the way you can do it from explicit format first, that's fine. You can do it either way. So you can start by saying, yeah. So you can start by putting this in your string, okay, before the for loop. So square bracket and a space, and then you're going to have a variable that will indicate whether it's the first iteration or not. So if it's the first iteration, you just print the number. But if it's not the first iteration, before doing that, before printing the number, you will print an extra comma and space. So if it's the first iteration, I just print a number, okay? Since now it's no longer the first iteration, when I go to the second iteration, of course, in the first iteration, I set my Boolean to false, saying, oh, it's no longer the first iteration. So next time I get in it, is it the first iteration? No, it's not. So I put a comma and a space, and then I print the value. Okay, that's one way to do it. Don't worry, it's only 15 past, so I can then show you live coding if you need, if you can't see. Perfect. But yeah, that was a bit tricky as well for me at first when I've seen the test failing. I've then compared the spaces and I realized they were expecting space in the very clear order. So everybody's fine with the first/second exercises? Very quiet, which I take it means you're working hard on getting that third one going. How is the third exercise going? Everything's going well, or something's going wrong somewhere? Sounds good. I'm about to lose the light again. Give me a second. Sorry for this. Seems the motion detectors are a bit hard not to detect me. Thank you. Roughly 20 past. Where are we up to? Anyone finished all 3 exercises? Nice, congratulations. Was there any challenge, or was it rather straightforward? Did you have anything you didn't see coming? Yeah, iterators are a bit confusing at first because you, as always with abstractions, there's a feeling that's a bit magical. We don't really know how it works behind the scenes. So when we're missing something, if it's in C, since we don't have any abstraction anyway, we just do everything ourselves all the time, which is not always a good idea, but typically the approach. In C++ or Python, yeah, when you have something that is abstracted, it may be a bit confusing to actually know how to do something specific, because there's probably a method in the iterator allowing you to do what you want, but it's not always easy to find. But yeah, iterator, const iterator, it's a matter of getting used to this notion of iterators, how to declare them, how to use them, how to customize them. Once you're past that point, then they become actually precious allies because they really allow you to inject code when you iterate through your elements, not by modifying the actual loop, but by modifying the tool you used to iterate through your elements. Because we might have someone in the audience say, oh yes, but if you want to inject some code, such as the monitoring idea you mentioned a few minutes ago, I can do that in my for loop, it's fine. Yes, indeed you can do that in your for loop, but now think of a 20 years old code or a 5-year-old code that is relying on the iterators in the for loops. If you have to update all the for loops in the code, that's going to be time consuming. If you just change the iterator themselves, you instantly have all the code updated for you. With a mapping, say, what are we actually doing? Implement AdWord. Yes, Lewis. So with the maps, you have to implement the function that I gave a bit earlier in the chat. So this function takes a map, which uses strings as keys and integers as values. And this map contains a string and the length of that string as a record. Identifier being the string, value being the length of that string. And you need to provide a function using the interface provided. Well, that must respect the interface provided. That will automatically append the new element to the map if it's not existing already. If it's existing already, instead of doing anything, you just return false. If it's not existing, then you insert it and you return true. I have experience with iterators in Julia. It's really just entirely getting yes. Is it by practice? Yes. No. In C++, yes, you can do this to avoid having to type std colon something. I must say I'm part of the people. It's not better or worse, it's just different. I'm part of the mindset that is not bothered with extra information. My function names, for example, tend to be long, but I don't mind. I just want them to be clear. Same with the std or the namespaces. I'm fine with the namespace. I want to make sure that I know what I call from where. Because when your code becomes more complex, you will have functions from different namespaces which can become a bit similar or might even actually be identical. So then to distinguish them, you have to use the namespace. If you happen to create a new namespace, and in this namespace, for some reason, you implement your own cout, then if you want to use that and the classic terminal, the classic standard output cout from the std, you will have to use std colon. So if you have, again, a big software that never used explicitly the namespaces, you will have to update all the occurrences. Whereas if it's already using explicit namespaces, there's no ambiguity because you know exactly from which namespace that specific function comes from. Again, it can be equally argued that it saves you time and it makes the code a bit shorter, so maybe easier to read by not having to redundantly using that namespace. You make your choice. Both approaches are valid. I go with the longer approach. You can go for the shorter if you like. But to answer bad practice, no. Yes, it's that's one of the reasons I do that. It's less and less I think of toy codes, and I instantly think of anything on a big source code. where there's already something that has been developed for 3 years, and we intend to use that code for 3 more years. And in 3 more years, we'll think of taking it in a different direction, but we'll have something else coming on top. The thing is, if we always take a simple piece of code made of 100 lines of code, we never have really a challenge in it. If we develop a tailored solution for a specific problem from scratch, and it will take 1,000 lines of code, fine. But if it becomes more complex and you have libraries coming from all over the place, in 6 months, there might be a killer library on GitHub from someone who developed a new way to print to the terminal using cout in a different namespace. And everybody's going to become crazy about it and want to use it. Problem, it's cout. That's one way to see it. Fine, yes, that's perfect. If you have access to a compiler that is compliant with C++20, you have directly a method called contains, which I don't even understand why it was not here in the first place. Such is life. So yeah, for now, find is the way to do it. But that's why, for example, you want to keep up, which is time-consuming and a bit challenging, but to keep up with the new features that come in every version, or to have an idea. Because, for example, if I show you vector, no, map contains C++. We'll go to the CPP reference. Okay, fine. And there's contains, but since 2020. So before that, you have to use find. Whoops, sorry for this. Where is it? Oh, okay, it's here. No, here. So best method before 2020, find. Best method after, contains. Best as in most convenient, but find will still do the job. Yeah, I never understood why it was not here in the first place. Contains. Maybe the semantics were not clear, or there was something, I don't know. We have less than 5 minutes. We have more or less 3 minutes left. So, oh, if you need to check if there's a key, count also worked for me. Oh, that's probably scales probably. Oh, the scale aspect of things is a whole domain in itself. Anything, and sometimes things we don't even suspect, can actually be very surprising when it comes to performance. Count type. The count type? Well, I would say that's an integer if you count. Scale poorly. Yeah, that's the thing. It's there's the operation that we can estimate, and we can have upper and lower bounds on the performance and the algorithmic complexity. But then there's the actual implementation behind the scenes. And an algorithm with a very smart and efficient algorithm might have a terrible implementation, and vice versa. So it comes down also to how well things are implemented for a given platform and so on. When we are using standard template libraries, the chances are it has been implemented in a very smart way on a wide range of hardware, using tricks you have certainly never heard of, that I have probably never heard of as well, either. So that's why we say here to use STL containers, because they're well established. They've had years or decades, or some of them, of optimizations. So typically something you want to do with them is done behind the scenes in a very efficient manner. I would need to see the code for this to actually see about this counts problem. More generally, since it's now half past, you're going to have your break. Do you have any question on the session in general? Was everything clear, or was there something that is still a bit vague or confusing, or was it okay for everybody? I would need to see more of the code. Are you on an M1 Mac, Josh? On a MacBook using M1 architecture? To clear these test expansion. Yeah, because you're the Ubuntu. Oh, okay. I don't know then. I will need to see more of the code again, getting more and more context. In the meantime, sudo, it's because when you have a vector that contains no elements, you're still supposed to produce a string with square brackets, and it seems you're producing a string with no characters at all. You're still required to pass these two square brackets, maybe even with a space in between. Yes, so you're expected to pass square bracket, space, square bracket. Yeah, sorry for this. I had a problem as well with a cache HPP, but it was because I'm using a Mac with M1, and it seems I had to update the cache version to 2.3.2 or something, and we need to double check this. So maybe it has to do with this, if we have anyone using a Mac M1. But in your case, it doesn't seem to be the case. Size of array out stack steps and integral expression. Yeah, I would need to see more lines. Sorry. Did it help Superall, by the way? Okay, perfect. So if we have no more questions, then I think it will be time for you to finish the exercises if you want. Otherwise, enjoy your break and get ready for the next session. Otherwise, time for me to leave you to it. Thank you for your time and continue to enjoy the training. Bye.
Okay, so I see that it's 3 p.m., so we can start. So the idea is we will have an hour left of today's session, and I will talk a little bit about resources. Let me share my screen. Also, please, if you have any questions in the chat, if you have any questions, please feel free to write them in the chat, because yeah, I can read them, I can have a look at them. Okay, first my screen. So can you see the slides? Yeah, thank you. So again, any questions, please let me know. Or also, if something is not clear, because I'm aware that you come from different backgrounds in terms of, like, some of you are more familiar with Python, Fortran, C. I would try to to explain this in general, but please ask questions in case that something is not clear. Okay, so resource management. What we will talk here is when we talk about the resources, we are talking about memory, about files, about, for instance, network sockets or database connections are resources that we will need to handle in C++. Here in this lesson, we will focus more on in memory. There are some, for instance, we need to handle memory also in Fortran. In Python is a little bit more transparent, but yeah, there was a question before in the previous session, what was the heap? Here is there is a representation of memory. When you execute a program, well, in this case, we are seeing that is written in C++, but it could be written in C, Fortran. When we execute a program, we request to the OS to run the program, and the OS gives some a chunk of memory. In the memory we have in the first part that is called text, data, VSS, etc. This is the okay. Now you can see the cursor. Here we have the instructions, and the data is stored here in the stack and in the heap, and also the all of these bytes of memory could be accessed by an address that is just a number. When we talk about the stack, is the memory that where we can define at compile time. So, for instance, we know the size and we can write that in the source code. When you run the program, this memory is allocated at the beginning of the runtime, let's say. And normally it's not here, but normally the stack is smaller than a heap. That the stack is used when you know beforehand the memory that like the variables that you will use, or some arrays that you will use. But it could be the case that you will need to allocate a big chunk of memory, or you don't know beforehand type, or you don't know the size. In that case, you will use the heap. Here also it mentioned that allocation and deallocation is faster here, and when you call a function, is updated. It's called the stack pointer. So you go to a new position of memory, so you are in another scope, in another context. This is a little bit, let's say, complicated. This is like a more related with operating system, but this information is here in case that you wonder how memory is managed at a low level. And also we have the heap. Heap is for dynamic allocation. So when in runtime, we need to allocate some memory, so we allocate that, and we get memory from the heap. And we get a pointer, that this is, when we talk about pointers, is a memory address of the memory that we get. In Fortran, this is like when we do allocate or deallocate. This is similar. We will see now in C or C++ how we can do that. Pointers in C++. This is when we check it. If you check other documentation, this is considered like a low-level memory management, because here we will see what is called row pointers, but later we will see more smart. I think are called smart pointers. Okay, so we have a piece of code that actually is pretty similar to code that we can have in C, but well, you see that the last line is C++ because use this standard libraries, or the standard way of printing in the standard output. We have an integer that is the value is 99. And also we define a pointer to that integer. To define a pointer, we use int and we use the star or asterisk. And to get the memory address of this variable, we use the ampersand. That means returns the address of memory where I is saved. So if we want to use the pointer, or we want to update the value that this pointer is using, what we are doing is we get the pointer and we use this star. This star or asterisk means the content of the pointer. So the pointer is, as the name says, point to a location in memory. So you are updating this the location in memory, and you are adding a 1. So when you execute this piece of code, the value of I will be 100 rather than 99. Is it clear, this example? Also, this syntax is the same for C, in case that you wonder. So I think this is similar when in Fortran when we use allocate or deallocate, and I think in Python you don't need to do that, because in Python the memories are managed in a, let's say, in a transparent way to the user. Yeah, no problem. I see that there is a question about the pointer of references. Yeah, I think the thing is, what the slide says that the pointer could point to a normally, yeah, actually pointer could point to a valid memory address, or it could be not a valid. For instance, if well, you see that here we have a pointer and we initialize the pointer to this to a random value. This is let's say we little bit, well, complicated. We will have an undefined behavior because we don't know if this memory address is a part of our memory space, or is a part of the instructions, or is part of the memory that is allocated by the OS. So here it will be like quite likely that the program will crash, because this memory could point to a memory space that is outside the memory space that we have allocated by the operating system. So the OS will detect that and will abort the software. Oops, sorry. And so when we do that, it will, most likely will crash, or we will have undefined behavior that we don't know what we are. I see that there is a question in the chat asking about the recordings. The recordings will be in the ARCHER2 training page, in the course page. Will be uploaded, if not at the end of this week, next probably next week. Thanks, Kevin, for the answer. We read that a reference and a pointer is not the same. A pointer is a variable that holds an address, and a reference is really just the address itself. Also here, you see that this function make a bad pointer is because when you are here in this scope, you define this variable. So this variable is defined in the stack. And when you return the function, this part of memory is no longer allocated, is free. So when you return this memory address, you are pointing to a memory address, sorry, you are pointing to a position in memory that is already free. So in case that you access that memory, you will have an undefined behavior. So it could be a crash, but also could be a silent corruption of data. You can modify some data that you don't want to modify. And could be data, could be, yeah, that will create a mess and will, the program will crash. So with the C++, normally when we allocate memory, we use new, and when we destroy, destroy the memory and we release the memory, we use delete. Thing in Fortran is allocate and deallocate, and also normally in C you use malloc or calloc and free. But this is a recipe for problems because we will see more about that. When we create, it could be the case that we want to create a class. So we were talking about constructors, but also is in case that we handle a resource. Again, we are focusing on memory, but could be a database connection, could be a opening a file, a resource. We would need to, let's say, distract or release the memory. Well, if we are talking about files, we will need to close the file. If we are talking about databases, we will need to close the connection. And this is when we have the class and we define several objects. So when the object reaches the end of the lifetime, we will need to release the resource that we have allocated. When it happens, so this is deterministic. So it's when a local variable goes out of scope, or when the object is destroyed, or when a programmer deletes them. There is an important note here that you should never call directly the destructor. Normally, the way of calling it is either using delete, or when the variable is this object is out of scope. When I mention out of scope is, for instance, in this previous case, when you call a function and this function returns, the object gets out of scope and the memory or the resource that we have allocated or is released. There is a pattern here explained that is RAII, that is resource allocation is instantiation. That means that when we define a class and we create an object of this class, when we call the constructor allocates the memory needed or opens a connection, opens a file, etc. And when you destroy the object, the resource is released. In this case that we're talking about is about memory. And we are following this pattern. This is done, let's say, transparent for the programmer. When I say transparent, it's in the sense that the constructor take care of allocating the resource, and the destructor takes care of releasing the resource. In case that you use a class that first you create the object, and then you need to allocate memory or open the file or etc., this class doesn't follow this pattern. That is a resource allocation, or in some places on the internet or in the literature, you will find resource acquisition is instantiation. So this is a example of this is a class that this is similar or emulates of a vector of double. Double is a double floating point number. So here in my class, I have two values. I have the size of the array, and also I have a pointer to double. That is data that I initialize it with the null. Null normally is like a zero value, so it's like a null pointer. So I have the default constructor. That means that the size will be zero and data will be null pointer. And also I have my array. This is a constructor that needs n as a parameter. So here I initialize size with the value of n, and data I allocate with new. I allocate a vector of size of a double. And here I define the destructor. That is when the object for some reason is destroyed, I call delete data. Well, I define this operator that here I return the. There is a question. Explicit means that because sometimes when you create an object, you can use different ways to create the object. But in this case, if we create an object of my array, you will need to use explicitly this constructor. So this constructor, unless that this is called using n as a parameter, would never be called. So if you search explicit in the here there is an example. Give me a second, I will show the. Yeah. So here we have two structures of two that we have A and B, and for instance, here in this case, I define an object A1 equal 1. So what the compiler guess that I will use this constructor, so it works. I will use this one. But for instance, here in B, because I specify this at explicit, when I use this, it will fail because it will not consider this as a default. So as explicit is a way to say that you cannot guess which constructor will be used. Here is better explained if you want to have a look. I will copy that in the chat. Yeah, it's a good question. Also, what happens, what I will do is now I will execute this class, and what happens when we compile and run this class. So I will, what I will do is I will, sorry, I will sorry instead. What I will do is I will share this other screen. Here I have my class defined here, class my array, and it's the similar that we have seen. The only thing that I have done is I have add a message here, constructing, and when the object is destroyed, it also prints a message. So if I compile and run this piece of code, this is what happens. So here I create an object called null, and I call my array, and this use this constructor, so nothing is print. But now I define the x, and I use my array, and here I define that the size will be 10. I will make this maybe a little bit bigger. Yeah. So what I'm doing here is I'm constructing, and I get this. This is the pointer. This is like the memory, the memory address of this of the first position of this array, of this vector. Well, array vector. I mean, I normally use like a. So I allocate that, and I get here constructing, and I print this. And then you see that when I finish the code, this is like a finish out of a scope. I'm releasing the objects. So I start like from top to bottom. So the last one that has been allocated is we are destroying this object x, that this is this address, and also we are releasing this null, that this is like the address is 0. There is a question in the chat that is about the lines 15 and 16. Here what I'm doing is I defining the square brackets. So if I call here, if I say x 5 CO, if I use this will call this function and will return the value of data. We are just redefining this. Yes, yes, a little bit. The problem here is when you use my array, and if you don't define this, you don't know what to print, because imagine that maybe you can have several pointers. So which one do you print? So you will need to here to specify which one is the one that you print when you use this operator. Actually, we can try and see the behavior of. So I think it will, yeah, will fail, because I'm not sure. Also, we haven't defined. Well, let's see if, but yeah, I guess that it will break. Sorry, it's STD. You see it complains, error no match for operator because it's not defined. I think it's because the function is not defined. It will complain. It will fail the execution. Okay, but the sample that I wanted to show is like if I do there's a question: you have defined operator will print a memory address? No, I will print. This data. Yeah, so what it does is returns the returns the value that is in the of this. Well, later I will check the questions are in case that something is not answered. I will. So with this example, what I wanted to show is what if I define if I use auto and I use another variable that is a y and I use equal x, what it will happen. If I run this code, it will fail. Why it fails? Because here I have three variables. I have null, I have x, and I have y. When I go out of context, y is released. So I destroy this memory address. But when x is released, again is released the same memory address. So there is an error because I'm doing a double free. And if you release the same memory twice, it will fail. And well, here is printing the stack. So this is what is happening when I'm. So how we can avoid that? So I will need to define we have defined the constructor, the destructor, and now I will need to define the copy constructor and copy assignment operator. What that means? Copy constructor is when I create a new object based on another one. So I have here x, where I specify the size, and here I specify another object called y, and here what I do is I'm doing a copy of the same object. That this is different to the copy assignment. That is when I assign a new value to an existing object. So I have x that here I have some memory allocated, size 10, but what I'm doing here is I'm creating another array and I assigning this to the same to x. So the problem is that the memory address that is pointed is in in X is lost. So I would need to first release X, first release this, and then allocate this in order to. We will see better a better example here. Also, this is all of these like functions needs to be defined when we allocate this when we do allocations of resources, because normally the compiler what it does is copy the memory address, but we don't want to copy the memory address. We want to handle the memory allocated that this address points to. So if we want to copy our array, we need to either copy the data, so do a deep copy, or share the data and keep track that the data is shared. So this is called a shallow copy. So what I needed to define here is how I copy this. So I will need to define these two new operations. So this is to copy this one is we will copy data from one object to the other, and this one I think this is like the copy initialization. No, copy. Sorry, I'm messing with the names. This is the copy constructor, and the copy assignment is when I'm assigning another object to a previous one. What I'm doing is I'm releasing the data of the previous object, and I'm allocating data for the new object. So this function is to when we do this, when you assign a new value to an existing object. So before we have 10, and now I want to allocate 2000. And I want to use the same object or the same object pointer. And here is I defined my array that is a set that this will be a copy of X. So that's why it's like a copy constructor or copy initialization. So for that, I'm using this function. What else? Also, here we have another this is like when here we allocate an answer that is a vector of integers, and I'm returning it. So what I'm doing here is in data, I'm creating a copy of answer. I'm saving it into data, and I'm releasing answer. The problem is, well, in this case, is not an efficient way of handling memory, because we are creating we have to book memory, do the copy, release memory, etc. So in this case, it's more intelligent to use the concept of move memory rather than allocating new memory, copying memory, etc. The thing is with C++ that I remember at the beginning I was usually say like the previous standards that doesn't have this defined, but since C++ 11, the language supports the concept of moving memory objects. That could be the samples are variables that are going out of scope, or also could be called explicitly using std move. So you move memory from one, rather than moving the memory, it's like you update the memory that has been already allocated is pointed by another pointer rather than. So it's here we allocate memory. So now rather than the memory, rather than the pointer be answer, that would be now data. And this is done. We will need to define this. We will need to define these functions to move data. Before you ask, this keyword that is called no except means that this function will never throw an exception. This is needed when we imagine that we use a container of this container that will contain objects of this class. Unless that you don't define this keyword, the memory will be copied rather than move. So that's why we are defining this keyword here. And here I have like several rules. That is the rule of 5. That is if you define or delete one of the following: copy constructor, copying assignment operator, move constructor. We have seen 5 functions. So we have seen copy constructor, copy assignment operator, move constructor, move assignment operator, and destructor. So it's the rule of 5 means either you need to define these 5. If you need to define one of them, it's pretty sure that you will need to define the rest of them. So if you define the destructor, it's very likely that you will need to define these other 4. Or if you define these 2, it will be very likely that you will need to define them. So it's like a kind of all or none. Either you define this 5 or not. And we come to the rule of 0. That actually that means that if there will be some cases that if you are not using, if you don't need to allocate some memory or open a file or do a database connection, it's very likely that you will not need to use this none of this. So this is what these rules said, that either you need to define these 5 functions or none of them. And this is what we call smart pointers, that rather than handling the memory by hand, like using new, delete, etc., these smart pointers, what they do is like they handle the memory in a smart way. And there are two types of pointers that we will see here. We see that we have the unique pointer, that the unique pointer means that this unique pointer means that only one region of memory could be only pointed by one pointer, so that was unique. So you see that the pointers could be moved but not copied. So you cannot have several pointers that point to the same region of memory. So this class unique underscore PTR, these copy constructors and copy assignations are not available, because it's a unique pointer. It's a region of memory that is only pointed by a single pointer. This could sound a little bit like a confusing, but yeah, it's like one of the, let's say, features of one of the C or C++ that you can handle memory at either a low level, that this is what we have seen so far, or you can use these smart pointers. And the way of doing that is for instance, working with the files. This is a class image that you open the file and you load an image to memory. And what you define is the function here, read image. Is like you give by you specify the file name, and you return with this function the pointer to this file name. So you can call it a read image cat, and you create this pointer. Also here I have some, this is to explain the difference, so that we can, if in case that we want to use these functions, that is x and y, the way of using them is either you can create use the reference and then use dot and the name of the function, or also this is the same. You can use the content of this pointer with the bracket and call the function. So that is the same. But also another way that you may find in some codes is when you use this arrow here. So this and this is the same. So using the arrow is a way of avoiding using this. Okay, we have seen the smart pointer, that is the unique, and also we have a share pointer. Share pointer is when we allocate an object, and this object could be pointed by by several pointers rather than a unique one. Also keeps track of how many pointers are alive, and when all of them, when they say that the counter reaches 0, the object gets destroyed. Also, there is an advice there that is if you don't need to use share pointers, it's preferred to use a unique one. This is a trick, just in case that for some reason you want your class to be able to get a shared pointer to itself. So this is the way of doing that. You will need to specify the class that is extension from this one, std enable shared from this, and also you need to define public. You need to define the function self, and the return you use shared from this. But I guess that is a function is defined here. Another point with this that you can create, well, this example maybe it's not that. You create you have a pointer, and there is a function that is called partner up. So you have two objects. So you get the let's say object A. You use a pointer, or let's say the partner of the object A points to object B, and the partner of the object B, the partner is a pointer, points to the object A. So if you define this, and when you execute here, you have two good and bad, two objects, and you create them with the std make share cowboy. So when you partner up, the problem here is that good points to bad and bad points to good. So when this goes out of scope, the memory will not be released, because they see that you are doing a loop. You are like one pointer points to the other one that points to the other. So you are here creating a little bit of a mess with with this loop. So here is some clarifications about the row pointers. Row pointers is what we have used before. Is when we use new, delete. This is called, we call again also like a low-level memory management. A clarification here that row pointers do not own resources, so we will need to specifically delete these resources that has been allocated. That with the smart pointers, these resources get automatically free when are out of scope. And also row pointers represent a single object. But also we can use row pointers in case that we want to call some functions and we want to send this. What I mentioned here, this again, other resources. We have been talking about memory, but we can also work with the files. Well, here is an example comparing Python with C++ to read a file. I think maybe in these cases you may understand why some people prefer Python rather than, because in C++, the thing is with, for instance, what we are today that is a little bit tricky about the memory management. For one side is tricky, but on the other side gives you a lot of freedom, or gives you like a lot of control about the memory that is allocated, released, and you can be more efficient with it. And again, this is for files. We use the resource allocation instantiation, because when we create the class file and when we use the constructor and the destructor. When we construct an object of the class file, you see that we use a handle and we open the file, and when the object is destroyed, we close the connection to that file. That's why we follow this pattern, or this pattern is a follow. If this pattern wasn't followed, we would need to do by hand the opening and closing of the file. Well, an exercise that you can try tomorrow morning or later this afternoon is the Morton order. Also, if you have some questions with the exercises, you can ask them tomorrow. I'm not sure yet. This part of the course is a little bit complex because we are handling memory at a low level. We are just to summarize a little bit. When we define a class and we need to work with a resource, we need to be careful both the resource that we allocate, that in the case of today's lesson is memory, to release the resource. Otherwise, for instance, imagine that you are using this, you are creating a lot of objects and you are destroying a lot of objects. So this memory that is allocated, that is in the heap, is never released. So you may see that sometimes the memory consumption increase, and never decrease. And this could be the case. Could be like there are some memory that is allocated and is never released. So for that reason, you need to be careful. If in the constructor you allocate some memory, you will need to define the destructor, and also you will need to define the other functions that we have seen, that is the copy constructor, the copy initialization, and also define the functions that move the memory in order to make the memory more, the object more efficient when you return the object from memory. Otherwise, you will do a copy rather than a move of memory. And for that, we have seen that how we can do it with row pointers, and also this could be handled with smart pointers, ARCHER2. That is a unique pointer. This unique pointer only the memory that is allocated is only referenced by this unique pointer, and at the moment that we get rid of the unique pointer, the memory is released. That's why it's smart, because we don't need to define the destructor. And also we have a server pointers, that at the moment that the memory that has been allocated is not pointed by any of these server pointers, the memory is released. We have seen also the patterns that the memory allocation is instantiation. That is, we should handle with these 5 functions that we have talked before, memory. And again, we are mentioning the rule of 5. That is, one of these 5 functions are needed to be defined. It's pretty sure that the rest of them should be defined as well. And also the rule of 0, that in some cases, if you don't need to handle any resource, you don't need to define any of them. So let's say kind of either all of them or none of them. Sorry if this is has been like a little bit like maybe quite hard for last lesson of last session of today. But please, if you have, we have now 5 minutes until 4. You have any questions or anything? I will check the chat if seems of if something has not been Yeah, there is a statement in the chat that is pointers are scary in any language. I agree with that. But on the other hand, once that you get familiar with them, could be quite efficient to handle memory. And one thing that I like, but well, maybe it's like a little bit biased opinion, with the pointers that you know what you are doing regarding memory management. At the beginning, maybe the learning curve is a little bit hard, but once that you are familiar with pointers, you can do things quite efficiently regarding memory allocation, the allocation, memory management, etc. Okay, I see that there are no more questions, so thanks for attending today. We will continue tomorrow at 1 p.m. My colleague James will keep explaining more features about C++. Have a nice rest of the day, and see you in these coming days. Bye for now.